Norma is CEO of Ashlon Energy up in Paynesville, and it's a company that provides multi-megawatt energy storage solutions using, and I have no idea what this is, Vanadium Redox fuel cells. That's one of the coolest things I've ever said out loud.
Nickel, the hidden metal in the batteries that power our world. Phones, laptops, electric vehicles, and large-scale energy storage systems all rely on it. Nickel is present in many of the new energy sources that are helping us move towards a more sustainable, greener future. But what role does nickel play? A lithium-ion battery is made up of a cathode, anode, electrolyte, separator, and 2 current collectors. When charging, lithium ions move from the cathode, which contains nickel, to the anode. When discharging, the anode releases lithium ions to the cathode, generating electric current. The reason so many electric vehicles are powered by nickel-containing batteries is because the metal delivers the highest possible capacity, with increased power and energy density, whilst being highly cost-effective. This allows the battery to be smaller and lighter, contributing to a longer drive range. In fact, nickel is the cornerstone metal in many battery types, each with different applications, including high-performance cars, trucks, buses, and even windmill and solar energy storage. And as new battery technologies are developed, nearly all of them have one thing in common: nickel. Its physical properties mean that it will continue to be an indispensable part of a greener, more efficient future.
What are solid-state lithium metal batteries? Let's start by looking at conventional lithium-ion batteries. A conventional lithium-ion battery cell consists of 3 main layers: a positive electrode or cathode, a negative electrode or anode, a porous polymer separator that keeps the electrodes apart, and 2 electrical contacts, 1 at each electrode. The electrodes are made of particles of material capable of storing energy. The entire cell is flooded with a liquid that serves as the electrolyte, which is the medium through which lithium ions travel. Let's zoom in to look at what happens inside the cathode electrode particles. Each cathode particle is made up of a lithium-containing metal oxide, such as lithium nickel manganese cobalt oxide, commonly known as NMC. These elements form a stable structure to hold the lithium ions when the battery is in the discharged state. As the battery charges, the lithium leaves the cathode particle and makes its way through the liquid electrolyte, passing through the pores in the separator on its way to the anode. There, the lithium enters the anode particle, commonly made of sheets of carbon, sometimes adding silicon. The sheets of carbon host the lithium until the energy is needed, with 6 carbon atoms holding a single lithium ion. Now let's see how solid-state lithium metal works. In a quantum-scaped solid-state lithium metal battery, there are only 2 main layers: a cathode, or positive electrode, with an electrical contact, and a solid-state ceramic separator, which replaces the porous polymer separator found in the conventional lithium-ion batteries. Where there used to be an anode, there is now just an electrical contact. The cell is manufactured without an anode. As the battery charges, the lithium leaves the cathode, traveling through the atomic lattice of the non-porous solid-state ceramic separator. Once the lithium is through the separator, it deposits between the separator and the electrical contact, forming an anode of pure metallic lithium. A lithium metal anode allows the energy of the solid-state battery to be stored in a smaller volume, enabling a higher energy density as compared to conventional lithium-ion batteries. Solid-state lithium metal allows for greater range from higher energy density, a 15-minute fast charge, and safer operation by eliminating the organic polymer separator. QuantumScape. The future is solid.
The Schmid Vanadium Redox Flow Battery consists of 2 tanks storing vanadium analyte and catholyte. Pumps are used to flow these electrolytes through adjacent half cells separated by an ion exchange membrane. Within the half cells, the electrolytes are chemically oxidized and reduced to reversibly convert electrical to chemical energy. An external electrical power source like PV installation supplies the energy to charge the Vanadium Redox Flow Battery. The 2 vanadium electrolytes are flown through the cell stack in which the electrical energy is converted to chemical energy. The electrolytes charged within the cell are flown back to the tanks, increasing the battery's state of charge. Looking into the cell at the molecular level, vanadium-3 and vanadium-4 enter the electrochemical cell. At the catholyte half cell, the vanadium-4 is oxidized to vanadium-5. This chemical reaction yields an electron which is drawn off by the conductive electrode material and a hydronium ion which diffuses across the membrane to the opposite half cell. At the anode half cell, the electron which has traversed the external circuit reduces vanadium-3 to vanadium-2. The hydronium ion which has passed the membrane balances the overall charge of the half cell. The 2 electrolytes leave the half cells in a charged state as vanadium-2 and vanadium-5. Once the grid cannot provide energy to the battery system, the Vanadium Redox Flow Battery swaps to discharge. Vanadium-5 and vanadium-2 ions carry the chemical energy into the cell stack. The chemical energy stored within the 2 electrolytes is converted to electrical energy, feeding the external load. At the molecular level, the reverse of the charging reaction occurs. Vanadium-2 is oxidized to form vanadium-3, releasing an electron which carries the electrical energy. For charge balancing, a hydronium ion crosses the ion conductive membrane. Vanadium-5 is reduced by an electron under consumption of a hydronium ion. The electrolytes leave the cell in their discharge states in the form of vanadium-3 and 4. The Vanadium Redox Flow Battery delivers electrical power until the electrolytes within the 2 tanks are completely discharged. The Schmid Vanadium Redox Flow Battery can be independently scaled for appropriate power and energy. Power can be adjusted through cell size and number. Energy is defined by the tank volume to perfectly meet the customer's needs. As the electrochemical reaction takes place in the electrolyte solution, no loss in power or capacity takes place due to side reactions as observed in conventional batteries. This fact ensures lifetimes superior to any other electrochemical storage. Even deep discharge does not influence battery health. Unlike other flow battery types, the all-vanadium redox flow battery incorporates vanadium in both electrolytes, eliminating battery deterioration through cross-contamination. The composition of the electrolytes, vanadium salts solved in dilute sulfuric acid, guarantees low hazard potential and best possible ecologic properties. With all these benefits in cooperation with low production costs, the Schmid VRFB is the appropriate means for renewable energy storage.